This is the game of life, and I made it in Scratch. And if you want to see how that turned out, you could just go to the end. But there's a lot of complexity to this project, and I just want to go through it for anybody who wants to improve on my designs or just learn something new. But the game of life is a cellular automaton, first made by John Conway. But it follows a set of 4 rules, which are: each cell with 1 or no neighbors dies as if by solitude, each cell with 4 or more neighbors dies as if by overpopulation, each cell with 2 or 3 neighbors survives, and for a space that is empty or unpopulated, each cell with 3 neighbors becomes populated. So it's called a cellular automaton. It's kind of like a living or physical virus because it's just population and survival. And once you break down these rules, things can get way more complicated. In fact, it's even Turing complete, which means it can run on itself, which you could see it doing right here. It's pretty neat. Obviously, that is far from what I did. But since I'm not a very good coder, I'm more of a block coder because I just can't visualize with physical writing code. It's hard for me to track. But I'll go through how I figured out how to do it right here. Let's just do this. Okay, so first off, the first thing I wanted to do is just start with the 3x3 grid. So I labeled these 1, 2, 3, and ABC, and so on. And I was initially thinking for my first try, very arrogantly, to do everything, just every possible option. It's like making a chess AI that's programmed for every single possible option. Ideally, in an ideal world with infinite memory, it would work optimally, but that's far from feasible because I did the calculations. It's just way too many possibilities. So what did I instead is I broke each cell into a array with its neighbors. So you can see that for A2, I cut it into this rectangle because this is all of the cells which I'm representing with these dots. Those are all the cells that are interacting with A2 or will ever interact with A2. And, for simplicity's sake, I have assigned variables and whatnot, and 0 just means dead and 1 is alive. This will come back later. But you can see that from these, in this case, A3 would have these surrounding tiles, and finally B2, which is right in the middle, has all of the surrounding tiles. But you can actually use this and the totals and which these each numbers are to your advantage to calculate whether it's a dead one, it's alive, it's about to get birthed, or it just phases out. So you could see that, if A2 is 1 and the total is 4 or more than 4, that means that it would be at least 4 bordering. Then A2 is equals 0, which means it dies. And we can actually use the same info to calculate, whether it lives, it dies, and so on. And it gets pretty complex, but that's generally what how I managed to code this. Otherwise, it would be way too complicated. But you can see, the specific functions. This is the basis of everything. But I did a few things to break it down a little further. So the first thing we need to know is, you saw that the alive cells were white. The alive dots were white. So there has to be a way for the code to know if a cell is on or off. And to do that, we're going to use a variable system. And we tie it in with the specific, in Scratch it would be called costumes, but the specific variations of a sprite. So I used 9 total sprites with 9 additional costumes, 2 for each one. One's alive and one's dead. And so I can tie in a value or a variable So A1 would be a variable, and you can see them in here. So if you can input them, and if it's A1 is 1, it's alive, and if A1 equals 0, it's dead. And then you can plug that into further functions to, create the logic system that makes this game work. And then let's take a look at the code before I mention everything else. So here's the code on Scratch, and I'll publish it so you can access it. But it's quite complicated. You see that there's a lot of different variables over here. I have one for each cell. Then I also have one for the generation number. So you can see the generation number over here. So generation 1 would be, after one sequence of, evaluation, what is it going to look like? And after that, it could do 2, 3. So it's iterative. So it's not going to be like immediate like these ones where everything's just flipping around. But that's because this is a very bare bones prototype, but I do intend to scale it up. But we'll get to that later. So for the actual code, the first thing we want to do is when the green flag is clicked, we know that, when the green flag is clicked, we definitely want the, let's see, so it's easier to see for everything. There we go. So we want the green flag to function as like basically a reset. So you can see if I'm clicking these 3 tiles and I don't want this, for example, not only do I want to set the variables to 0, but I also want to see that reflected in here. So I put in a function for that. Also for the sprites, I just made a function for that. So when you click them, it sets the costume. You can see the costumes here, which are dead right here and alive. It sets them up so you can see them. And so a lot of the actual physical properties of the code, it's all about broadcasting specific messages. And that's another thing that needs to be got into. So there's a variety of different messages that I use, 1A dead, 1A alive, 1B dead, and 1B alive, and so on and so forth. And that allows me to make this more simple because then I can break things down. The big chunk of the code is right here, and I'll get into that. But also, in addition to that, we have each single sprite tab just has when I receive these messages, I first set 1B to, in this case, 1B to alive or dead, and the costume as well. But you'll see we also have the finish generation sequence variable right here, and that's to coordinate. Because if these happen one at a time, it's not going to be one singular generation of things. It's going to be, they're all going to like work within each other and interact with each other throughout the whole thing. And we want things to switch immediately. Because if A1, for example, calculates immediately, and then A2 checks the different things around it, and then also changes, and that changes A1 again, or AB downstream. We need to make sure this all happens at once, just so it doesn't get tied up. And to do that, at the very end of this whole string, we just have a set finished generation sequence to 1. And so for all those messages, when they go out, it has to wait until that gen sequence goes to 1, so you can see exactly, you need to see exactly when it starts and it snaps and everything comes into place. Because that was initially a problem I was having where things were turning out really weirdly. And then here's the complex stuff. So if you look at it, it looks bad, but it's really pretty basic. So in this case, we're doing 1A. So if 1A is 1 or alive, and its surrounding neighbors are, if there's too many surrounding neighbors, or over 4, which it's 1 more than normal because it also includes 1. Because in this case, it would look like this. Then it would mean that, well, you can actually overpopulate a corner, but let's do 1B, for example. actually, they're all condensed into one singular thing. So here's 1b. So you can see we have 6 different variables. So if we click all of them, you'll see that as long as there's too many and it comes overpopulated, when I hit the space bar, you can see that 1b turns off because it was overpopulated. And I just keep doing this with each one. You can just look back at the notes that kind of details more of this process. But yeah, so 1b right here, that's for overpopulation. This is underpopulation. This is for dead cells that get revived when they have 3 right next to them. So you can see that, like, this is 3 right here. So this one should light up because it has 3 neighbors. And that's exactly what happens. And look, you see that they're a stable population because you can see these squares actually. In the others, you can see a lot of them right here and here because it's stable. It's completely stable. Because each square is touching 3 others and no other squares. So it doesn't get overpopulated, it doesn't generate new ones, it just stays the same. So you can see the generation counter right here. And as I continue to increase the generation, there's nothing that happens. But we can hit the green flag to reset that. And then we also have to include not just the underpopulation and overpopulation, the revivals, as well as the final one, which is basically whether if you have 3 neighbors or 2 neighbors, you'll be fine. So this guy has 3 neighbors, and you can see that he stays alive. But for this one, who has 2, you'll also see that they stay alive. So that middle one right there stays alive. And then lastly, let's do this one. This middle one is not going to stay alive because it only has 1 that's bordering it. And you can see that dies out, just like the other one. So it's really neat. That's basically all it is. But I repeat that for every single variable and for every single cell. And it sounds tedious because it kind of is. But the nice thing about Scratch is you can actually see people's code and what they did. So it's, if you want to improve it, there's not much that you have to do besides, well, that's one of my focuses, is for it to be scalable. Because this is just a prototype. So this is just a prototype. So this actually is scalable. So even though it's a lot of code, if you just keep copying the code, you can expand this square bigger and bigger until something this big would probably crash my computer, but something big enough to be kind of a cool thing to see. It's pretty neat. One thing I really like that I really wanted to see as kind of a test to make sure it worked is these oscillators. So you can see that there's 2 different stable positions, and I really wanted to see that reflected. So let's go 1 down. So you can see this guy in the middle, he's got 2 neighbors, so they're gonna stay alive. This guy has only 1 though, so they're gonna go away just like this guy. But this one right here, which is B1 and B3, yeah, B3, they each have 3 neighbors, so they're gonna regenerate. So, once we press the space bar to initiate the first generation, you can see that it changes. And, once it's flat, the same thing happens and it just keeps going. And I was really happy to see this work. One thing that you can't see in my code that I do recommend, there's these sound tabs. Here's one. Yeah, it's pretty interesting. It's start sound, it's a meow. And I didn't use that in any parts of my code for my final build, but for the initial parts, it's good to test to see what works. There's a lot of problems when you're coding to see the process of elimination to see what exactly is failing. And I use that. So if I heard the meow, I would know that the code actually got to that point. So, you can kind of use it as a basis, like a pin of where you are and where the code goes to. Because there's been times that I've had one of these numbers wrong and it screws everything up. But other than that, it's pretty neat. And I recommend anybody to expand it, try their own thing. It's a really cool, interesting project. And I, yeah, I'm very proud of it. And in the future, one of the other things I'm going to do for like a slightly larger one with larger oscillators is to have it repeat. So there's like forever loops in here, forever right here. And you can put that on and it would repeat forever. I mean, there's ways of doing that, but like wait for 1 second so it doesn't go into a blur. But there's a lot of interesting ways to take this, and I'm by no means a scratch master. I 2 days ago is when I first got on this platform. I'm just so bad at coding. Otherwise, I just like the blocks. But overall, it's a really neat project. It's really cool, and I'm very happy about it and how it went. And it's a good guide for more other cellular autonoma that have other rules that you could try to do a different thing with. And I'm glad I got to share this with you. So thank you.